I first want to show you some of this, which is at first very qualitative. I don't want it to become quantitative yet. The difficulty with these experiments are, I'm going to use this plank here, that the moment that my fingers touch this plank or touch the bottom of any of the objects that I'm going to slide, then all hell breaks loose. A little bit of water on the plank would locally make the friction coefficients larger. My fingers have chalk on them. A little bit of chalk on a local place would make the friction coefficient go down. That's why at this point we'll keep it a little qualitative. The first thing I want to show you is if I take a rubber puck and I put a rubber puck on this incline and I have a plastic bin, which is quite smooth, I put it on here, that it's immediately intuitive that the friction coefficient of this plastic bin will be lower than of the rubber puck. So when I increase the angle, you expect that first the plastic bin will start to slide and then the rubber puck. And if I gave you the angles at which that happened, you could actually calculate the two values for the friction coefficient, which I will not do now, but I will do that later. So all I want you to see, I hope, that this one will go earlier than that one. So I'm going to increase the tilt. I do it very slowly. I try not to rock the boat too much. Very slowly. We must be approaching the critical angle for the plastic. Boy, it's holding on to itself. There it goes. And the rubber goes a little later. The rubber can be made rough by rubbing it on one side, in which case the angle will be even larger. I told you that the friction coefficient is independent of the mass of the object. I have two identical bins here. Well, as far as they can be identical. Maybe one at the bottom is a little rougher than the other. But in one, I'm going to put 200 grams, which is about 5 times the weight of the bin. And then, within reason, when I tilt them, they will go at the same angle, because it's independent of the mass. So let's try that again, and see how close they are. It may be off by half a degree or 1 degree, of course, because the plank is not uniform everywhere. And now it's 18 degrees, 19 and a half, 20, 20 and a half, 21, and the other one is 21.2. So they almost go at the same time. So you've seen that apparently the mass has a very small, if any, effect. Now comes something that I always find very, very non-intuitive, and that is surface area. I have two pieces of wood, and they're identical, whatever that means, identical. You can never make them exactly the same in terms of roughness. This surface we prepared as well as we prepared this bottom surface, but this bottom surface here is 4 times smaller in area than this surface here, the flat part. I'm going to put the flat one here, and I'm going to put the same object, but with its small area here. If indeed the friction coefficient is independent of surface area, then when I tilt them, they should start to slide roughly at the same angle. There we go. 14 degrees, 16, 18. One goes, and the other one follows, within 0.2 of a degree. And the reason why there's always some difference, of course, the plank is not exactly uniform. I have to be careful that I don't touch the critical surfaces. So you have seen difference in friction coefficients, and you have seen there's almost no effect on surface area, and there's no effect on the mass. And that is both very non-intuitive. The width of the tires of your car does not matter. And that I asked you the question to explain in your assignment number 3, why race cars have very wide tires. There must be a reason for that. I want you to think about that.